All right, we are in section 1.2, talking about algebra and composition with functions. So, given two functions, f and g, with a common domain, we can define any of the following functions: f plus g, f minus g, f times g, and f over g. So basically, we can perform algebraic operations on functions. So if you have two functions with the same domain, you can add them, subtract them, multiply them, divide them, assuming that the bottom of the fraction won't be 0. That's a little caveat for division, but this allows us to kind of expand the types of functions that we work with, and obviously start combining functions. So let's take a look at an example. So we have f of x is 4x minus 3, g of x is 4x squared minus 7x plus 3, and h of x is x minus 1. We're going to find f plus g, f times h, f times g, g over f, and then we're going to find evaluations of those for specific numbers. So we're going to start off with f plus g. So we're going to have f plus g, and then we can try to just combine any like terms that we can. So let's see, we'll have 4x squared, we have a 4x minus a 7x, so that'll be minus 3x, minus 3 plus 3 is 0. So that would be f plus g of x. Okay, that's the sum of those two functions. For f times h, we have 4x minus 3 times x minus 1. So we need to multiply this out and distribute. So you can think about this as like foiling, if you remember foiling from algebra. So you have first, outer, inner, last. You have to multiply all those terms to each other. So we're going to get 4x squared minus 4x minus 3x, so that's minus 7x. Negative 3 times negative 1 is plus 3. So that's going to be f times h. For f times g, we get 4x minus 3 times 4x squared minus 7x plus 3. And again, we need to distribute, so the 4x is going to get multiplied by all 3, and the negative 3 is going to get multiplied by all 3. So we're going to get 16x cubed minus 28x squared, and then minus another 12x squared, so that's minus 40x squared. Then we have plus 12x, and then plus another 21x. So that's going to be 12 and 21 is 33. And then minus 9. Okay. And, if you're still kind of warming back up into these algebra topics, you can go term by term, right? Write everything out and then combine like terms afterwards, and that's fine too. Let's see. So g over f, we're gonna have 4x squared minus 7x plus 3 over 4x minus 3. Now the question is, can this be simplified at all? In its current form, it cannot, but we can try to factor the numerator here, factor this formula. It turns out it does factor. It factors as 4x minus 3 and x minus 1. Right, and that's actually, we saw that back up here, just kind of in a different order, over 4x minus 3. Now, when it comes to canceling terms in the numerator and denominator of a fraction, you can't cancel across like addition and subtraction like this. So like I couldn't just go like this when they're being added and subtracted to each other. But this one, I have this whole expression times this whole expression and then divided by this whole expression, right, as a whole. So we can actually cancel this entire expression with this entire expression, because this is a multiplication problem, not an addition and subtraction one up here anymore. So all we are left with is x minus 1. That's our fully simplified version of that. And now the kind of part 2 up here, it's asking us to basically evaluate all of these for specific numbers. So we're going to have f plus g of 2. That's going to be 4 times 2 squared minus 3 times 2. 4 times 4 is 16, minus 6 is 10. F times h of negative 1. We get this. That's 4 plus 7 plus 3, so that's 14. F times g, of 0. Well, this is going to work out pretty nicely for us. That's going to be a 0 minus a 0 plus a 0 minus a 9. So we just get negative 9. And then g over f of 5 is just going to be 5 minus 1, which is 4. So we get these new functions, right? These new formulas created using algebraic combinations of the previous ones. And then we can evaluate those just like we would any other function, okay? Just like the functions we've seen previously. So we can perform algebraic operations on these functions. We can also do what is called composing functions. So composing functions, or taking the composition of two functions. So taking the composition of two functions is denoted using this symbol, f of g, but it can also be written like this, where you have f as kind of the outer function, and then g as that inner function. So in this composition, elements in the range of g act as the domain of f. So in other words, the outputs of g are the inputs of f. Okay. So if we look at this kind of on our input-output kind of diagram here, like we've seen before, so we have x, and then we run that through g, and we get g of x, whatever that result is. Then we take that and run it through f, and we get f of g of x. So x over here is the input, right? That's the independent variable, the one that goes in the first place. Once we run it through g, this becomes the output of g, but we're about to take it and use it as the input for f. So it's kind of pulling double duty. It's doing both. The output of G is acting as the input of F, and now the result we get out of that is our complete output, our final output. Okay, so when you have a composition of functions, you have one function inside of another one. Okay, so you run x through the inner function, and then whatever that gives you, you run that through the outer function. One thing to note that's particularly important, in general, f of g of x is not equal to g of f of x. Okay, so taking f of g and g of f generally are not the same thing. There are cases where they are the same, but as a general rule of thumb, we should not expect those to be the same thing. So let's take a look at an example. Top of the next page here. We have f of x and g of x. We're going to find f of g, g of f, and then we're going to evaluate f of g at a specific value. So we have f of g of x. So we'll rewrite it as f of g of x like this. And now what I want to do is I want to replace g of x with its formula. So this is f of x squared minus 2x. And now this is the input for f. So remember in the last section we looked at, you can plug in all sorts of things, not just numbers. You can plug in expressions and different variables into a function. So this x squared minus 2x is replacing x in this formula, just directly substituting in. So this is going to be x squared minus 2x plus 5. And that's pretty much it. There's not much more we can do to that. And that would be f of g. And then if we want to find g of f of x, now the roles are reversed. So g is the outer function. Now f is the inner. So x plus 5 is going to go into g. Okay, so x plus 5 now becomes the input. So it's going to replace all of the x's in g. So this is going to be x plus 5 squared minus 2 times x plus 5. Which will give us x squared. We get plus 10x minus 2x, so that's plus 8x. And then plus 25, but minus 10 is plus 15. And then it asks for f of g of 3. Now, luckily, we've already gone through the whole process of finding f of g, so we don't need to do that again. We just need to substitute in the given value into the general formula we already found. So 9 minus 6 plus 5, 3 plus 5, that is 8. All right. The last thing that we're going to look at in this section, we're going to look at a little bit of application that's going to come up periodically throughout the semester in the realm of like business and economics, and that is revenue, cost, and profit. So we have some formulas, some relationships for these concepts, and we're going to be applying these to functions, and we're going to be working with them periodically as we develop more techniques. So First thing to look at, if you're talking about the cost of an item, the cost of a product, cost is broken down into two pieces. There is the fixed cost, okay, your fixed costs. These are costs that you're going to have to pay as a company no matter how many products you make. These are things like your overhead, a certain amount of like labor or whatnot, materials to get started. But then in addition to that, you will have the variable costs. And these costs can change depending on how much you're making. So if I'm, running a lemonade stand, I'm going to pay for my table no matter how much lemonade I sell, right? And I'm going to pay for my equipment no matter how much lemonade I sell. But if I want to sell 100 glasses of lemonade, I'm going to need to buy lots of lemons. If I'm going to sell 1,000 glasses, I'm going to buy even more lemons. The cost of those lemons is going to change because I'm buying more or less. So that's what makes it a variable cost. So the cost is the money that we're losing that's going out. The revenue is the money that's coming in. So to calculate revenue, we take the number of items sold times the price of each item. And typically, for the number of items sold or quantity, we call that X, and the price is P. So typically, we get the formula X times P for revenue. So revenue is the money coming in. So if I sell, again, 100 glasses of lemonade, and each one costs $2, 100 times 2, I've made $200, right? In terms of profit is the amount of money that you get to keep, basically. So the revenue is the money coming in. The cost is the money going out. So you take the money you make, subtract off the money you spent, and what you have left over is your profit. That's how much money you get to keep. Okay, so profit is a relationship between cost and revenue. So this is why we talk about it in this section, because now you have an algebraic relationship between two different functions that is used to create a third one. Okay. So let's take a look at an example. So a manufacturer of phone cases determines the number of cases they sell each week is related to their price by the equation x equals 1,300 minus 100p, where x is the number of cases and p is the price per case. What price should they charge for each case if they want their weekly revenue to be $4,000? Okay, so they want revenue to be $4,000, and it's asking us about the price, right? How much should they be charging if they want to make $4,000 a week in revenue? Well, revenue is X times P, right? It's the number of items sold times the price. We don't know the price, but we do know that the number of cases that they sell is given by this formula. So we're actually going to substitute in this formula into our revenue function. So this is going to be 1,300 minus 100p times p. And they want their revenue to be $4,000. So we're going to go ahead and set that equal to 4,000. So again, this is revenue equals 4,000. And we're trying to solve for p. There's a couple in here. So when it comes to solving this now, the setup is done. Okay, so we've read, interpreted, and we've applied the proper formulas. Now this becomes basically an algebra problem where we need to simplify this as much as possible. So we're going to get 1300p minus 100p squared equals 4,000. Let's make these numbers a little smaller. Everything in here is divisible by 100. So let's get rid of a couple zeros on all of these. So we'll have 13p minus p squared equals 40. So we'll move everything to one side. So I'll move them so that the p squared is positive. P squared minus 13p plus 40 equals 0. And then we can solve this using any of our means of solution for a quadratic like this. Factoring is probably going to be the easiest, but you could also use like quadratic formula. You could use completing the square. So we have several different methods that we could use. But this one does factor pretty nicely. You want two numbers that multiply to positive 40 and add to negative 13. So you're going to get p minus 5 and p minus 8, which gives us two values. We get p equals 5 or p equals 8. So these are both p values. Okay, so these are both prices. And the question was, what price should they charge for each case if they want their weekly revenue to be $4,000? So we can say to make $4,000 a week in revenue, they should charge $5 or $8 per case. So those numbers would give us a revenue of $4,000 based off of the information that we have and the formulas that we have. So as you can see here, again, we're just applying the same function ideas, the same algebra techniques that you would have seen in the past, just now putting it in a little bit of a context. Okay, we're adding dollar signs to numbers now, right? So we're just adding new stuff on top of the old stuff that we're familiar with. But that brings us to the end of section 2. When we come back in section 3, we're going to be talking about a little more graphical interpretations with functions. And we're going to start making that transition into more calculus topics over the next couple of sections. So I will talk with you all in the next one.